So we're switching gears a little bit here, and we're talking about explainability and why is it, this kind of main way to fairness, accountability, and trustworthiness of clinical AI. Well, AI in general, but of course this is much more prominent in clinical applications. So this is me. I work as part of the biomedical informatics lab, Mario Stefanelli in University of Pavia, and those are my main research interests. So let's start from the beginning. Why should we really strive for AI explainability? I put there just 3 icons, which represent kind of healthcare, criminal law, or something along the likes, and finance, right? So all of these have in common is that it's high stakes domains. And this is where it's kind of paradigmatic that people are pushing for, okay, we should have explainable AI, right? The other reason is because there is this, which is kind of a misconception, but embedded in the European GDPR, there's this concept to a right to an explanation when some automated or semi-automated decision-making process is happening behind the scenes. This is not really true, but I urge you to read this small piece from Sandra Wachter. She's a prominent scholar at Oxford, and she's the one behind the whole concept of counterfactual explanations that you might have heard of. She's not a technical person, by the way. She's in law and philosophy of science. So just to be clear, explainable AI is often sold as a kind of a new trend, but it's not really new, at least, and it is not new at all, I would argue, in biomedical applications, right? And this is, you can see it very clearly in this example. That's 1975 at Stanford University, and you see a very young version of Ted Shortlift that a few people in the room might know. Of course, Stefan does very well. So Ted was trained as an MD, and then he went on to have a PhD in computer science at Stanford University, and he was one of the pioneers in AI applications to the medical field. And his PhD dissertation was around this mycin system. This was still not really machine learning. It was, they were called expert systems. So it's based on a formalization of rules that would codify medical knowledge, and that there was reasoning happening behind the scene. And the whole point was to try to select a proper antibiotic to treat some bacterial infection or viral that the patient would have. And if you look closely, here is just some, Easter egg. It's still available and functional. You can fetch the Ruby implementation that works in nowadays computers. And if you look in the original paper, well, this was the architecture, and you find a very nice block here that is all around explanations to the final physician user, right? And look here, wow, this is with natural language. Wow, this is really fast forward to nowadays, right? LLMs weren't really a thing back then. So it's not a new trend, because when it's a high stakes decision, you gotta embed explanations on the internal workings. And of course, it's much easier to do that if you have an expert system where you can inspect the rules that were activated, and I'm talking if-then rules, and follow the chain of thought and see why exactly the system was suggesting this for my specific case. But fast forward nowadays, of course, it's explainable AI tends to be very easily equated, and I love to be speaking to a crowd where these double equal means something to all of you, because it's not always the case. Okay, we have SHAP, which is an elegant, very, I think it was a great idea based on game theory to kind of do feature importance attribution, okay? So it's also model agnostic, so I have now Shapley values, and I can explain any prediction of any AI-based model whatsoever. So, okay, SHAP and explainable AI, okay, this is problem solved, right? It's by far the most applicable approach, and there's libraries out there from Microsoft Research. It's excellent work. But I would argue that this is kind of we're going too fast here, right? So, and I would try to elaborate a little bit on the why. So it's nice to go back to the dear old saying of George Box that about modeling in general, and he was talking about statistical modeling, but I would argue it's no different from ML-based or AI-based modeling. All models are wrong, but some of them are useful, right? So I think that the fundamental question we should ask ourselves is why are we even building these models? And let's talk machine learning models in biomedicine and healthcare. So the why is the driving force and makes all the difference in the world. And another excellent pointer, sorry, again, it's a stats paper. It's kind of technical, but I think it's all about this. So there's Dr. Shmueli, also, I think from Stanford, if I remember correctly, has this excellent paper, which is, it's all about why you're building the model. Is it to explain or is it to predict? And this is some kind of fundamental underpinning that then makes the whole difference on what comes next. So I would say in science in general, and so much in biomedical sciences, we either build a model to understand the process that we don't know the internal mechanisms for. Okay, it's too complex. I don't have differential equations, whatever. My fancy mathematical modeling cannot explain this to a point where I can build prediction on or find the underlying, rules of nature, right? I cannot run an experiment and find out Newton's law on some complex, internal workings of your endocrine system. So you build a model and you come up with factors that account to so much, looking at the data, right? And it's a kind of, so you do that to do KDD, knowledge discovery. That's what you're after. You're after explaining these complex phenomena that otherwise you wouldn't be able to grasp. Another thing is I don't care about the why. I'm not trying to distill some knowledge out of these complex beasts that I'm not able to observe. I'm just trying to find something that just works, okay? And I think this is fundamentally different. I want to be able to forecast for my, biological signal. I don't want to know why the heart rate will be dropping in the ICU. I just really, really, really want to know when this will happen 2 hours in advance. Okay, and this is a different undertaking, I think. Also, another argument, and I think Professor Cristianini, he works at he's Italian, of course, but he works in the University of Bath. He has this nice book out. It's kind of recent, and he's touring around all the good institutions in Europe and US to spread the word. Where the whole thing, so the book is called The Shortcut. Okay, should we really be so obsessed in our systems mimicking the way of reasoning that the human has? Probably no. And we have a few examples. Many courses, at least in my institution again, for example, they're about the biomimetic system. So the course on neural networks would be called the biomimetic system. So you'd start from the paradigm of neurons, and then this is an artificial neural network that is built to make the brain and all that. But it's not really like that, right? It's just some parameters in high-dimensional space, and okay. So I think it's about time that we drop this bond when it's not needed. I'm not saying that we shouldn't be so attached to this fact that this artificial intelligence should work exactly the way that the human mind does. And I think we had very good examples in the recent breakthroughs of natural language understanding, where some computational linguists that went down the language modeling in the traditional sense, where they would try to devise the rules that govern the generation of text and spoken language, and they didn't achieve such great results. as those people that forget about it, we're just going the statistical way. Okay, and this is what it's all about. Is that explainable? No, of course, but do we care? Maybe not all the time. Again, there's also another very interesting trend, and I'm citing Frank van Harmelen here from Amsterdam Vrije University, and this, I think, it's a very good trend that is worth looking at, and it goes under the name of neurosymbolic artificial intelligence. So it is kind of trying to merge the best of both worlds. And why I'm mentioning this, and Frank also, well, he's a prominent scholar in semantic web, but he has a keen interest on biomedical applications, because the special thing about biomedicine is that there is so much prior knowledge that we really cannot just forget all about it and just do the purely statistical and data-driven way, I think. Otherwise, we would be kind of rediscovering something that is already embedded in our books, or whatever, clinical gestalt and all this, right? So I think that combining the symbolic way and the semantics and the richness of biomedical resources that we're used to handle, we've seen excellent examples about clinical guidelines from Stefan, or controlled ontologies and terminologies and all that, and bridging that with the whole neural-based and machine learning kind of things that we do nowadays, for example, in the embedding state, and switch our perspectives here and there for whatever works best, right? And here, Frank, you can look up this talk. It's on SlideShare. He has very good examples of a few things that happen better in this space, in the vector space, and a few things that you really need the semantics bit to achieve. So this is maybe something that is the best of both worlds. It's still happening right now, but I think it's an interesting space to keep an eye on. Then this is all to say that sometimes it's important to have an explanation, and it's good, and I think it will make a real difference to gain the trust of the users and to foster pushing all of these from the research setting to the clinics and stuff. Because the users we're really talking to have, they're trained differently from us, right? And they need to partner and to be on board for these kind of things to either to really make it into practice and to make a difference. But here is a very good example. This is out of Mayo Clinic. It was a ginormous study where they had 500,000 digital ECGs, and this is after the cleaning and dropping some of the stuff that they couldn't use. And this was kind of a standard 10 seconds ECG that you get every time, right? And they were able to build a deep learning-based classifier that would be able to detect atrial fibrillation. Probably not all of you are well-versed in cardiology. So this is called a paroxysmal condition. So it comes and goes, it doesn't really, and it's also the most prevalent arrhythmia for 50 years old and older, okay? But you never know if you have it until you can catch these 10 seconds when you actually are having an episode. And it's not predictable, so it's a tricky diagnosis, okay? And they were able to build a classifier with this kind of performance, so AUC over 90, that would tell from a clean piece of ECG if you have AFib or not, okay? And this is not something that a physician could do. If you give whatever best cardiologist, electrophysiologist in the world this piece of ECG, he would say it's normal sinus rhythm. But this thing, it's picking up some different kind of signal that is not available to the human understanding, or just eyeballing this thing, and not even Medtronic and all these producers could do this with their own machinery for Holter monitoring and all that, but they can achieve this. And this is, I think, through discovery. And it's thanks to the machine working in a fundamentally different way than these doctors were. Okay, so all of this, not to say that explainable AI is hopeless. We are doing something in this space. because healthcare, again, should be handled carefully. So we have our own post-hoc explainability kind of a method. We assess reliability of machine learning prediction when you're predicting on some out-of-distribution sample compared to your training data. And we have a few things that are examining the data set shift. For example, there we have a work on how COVID prediction algorithms worked across the waves. Okay, and then I think I'm out of time, but this is just a sneak peek, so I'll be happy to connect afterwards. We're studying how explainable AI, instead of just AI, is modifying the naturalistic decision-making process of doctors. This is a not very technical project, but we're more interested in the psychological and really decision-making process that is behind it. And we have an excellent team of psychologists behind us. We're looking into different paradigms, so not just explaining your prediction, but kind of keeping the control of the decision in the doctor as much as possible, but just presenting reasons for and against a certain decision. And of course, here it's a binary decision, like these two, Angel and the two different advocates for two different things. And we're also trying to build our own explainable systems. And we have an example here on coronary CT scans and why you should have a look at this patient with mild or not mild risk, a little bit of textual explanation, and also together with the confidence of the prediction with this. And I think I will leave you with this. It's still TED a few years later. You know, the guy from Meissen, it's the same thing. And he recently gave this keynote in a Medical Informatics Europe conference saying that a doctor that fears being replaced by AI probably deserves to be. And here I elaborate a little bit, building on Zach's point on what this really meant. Okay, thank you.
Thank you, Enea.